Good morning, friends. It gives me immense pleasure to be here again for my favorite course, Engineering Thermodynamics. I am Dr. Dwivedi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have covered the Module 1, Module 2. Now I am in the Module 3, which is related to the properties of the substances as well as molecular diagram, psychometric chart, refrigeration environment. These all things will be covered in this topic. Today's my lecture is on the properties of the pure substances. In this, we have, these are the contents for this topics, that is introduction to syllabus for the module 3, pure substances, phase transformation, temperature and entropy and enthalpy and entropy, HS diagram, TS and HS diagram, introduction to molecular chart, PVT surfaces, triple point at critical state, properties, and dryness fraction. These topics I am going to cover in today's lecture. This is the syllabus for the module 3, that is pure substances, phase transformation, TS and HS diagram, PVT surfaces, triple point at critical state properties during change of phase, dryness fraction. Up to dryness fraction I will cover. Then I will see in the next lecture I will cover the molecular chart, psychometric chart properties, dry bulb temperature, wet bulb temperature, dew point temperature, thermodynamic wet bulb temperature. These all things I am going to cover in my next lecture. So first we have to see what is the pure substances. So pure substance, a substance that has a fixed chemical composition is called the pure substances, such as water, air and the nitrogen. A pure substance does not have to be of a single element or the compound. So a very good example for this is milk and the water. The milkman comes in your house and he's telling that this is the milk, but mostly 30 to 40 or 50% there will be the water. So it is a pure substance. If you mix, it will becomes the homogeneous. So a pure substance may exist in different phases. There are three principal phases. They are the solid, liquid and the gas. As we know that solid, liquid and the gas. These are the three phases of the substance. Okay. So a pure substance may exist in different phases. Like if you see the water, water can be solid as a ice, it can be water as a liquid, and it can be a dry saturated steam like a gas. So a pure substance, it can transform from one phase to another phase. So what is the phase? A phase is defined as having a distinct molecular arrangement that is homogeneous. So this word we have to very much, if anything is homogeneous throughout and separated from the others. So, and if by easily identifiable boundary surfaces. So a phase is defined as having a distinct molecular arrangement that is homogeneous throughout and separated from others, if any, by easily identifiable boundary surfaces. So boundary surfaces should be very much clear, that water and the ice. This you can see, that on top of water you have the ice, and if you boil it, it will become the gas. But water and gas, it will be clearly visible. So that is the definition of the phase. Phase of the substances, we have the solid, liquid and the gas. Just now I have described. So what is the solid? The solid, in the solid, the molecules are arranged in a three-dimensional pattern that is called the lattice throughout the solid. The molecules cannot move relative to each other. They are very closely packed. All molecules they will vibrate. They will not move to their position. However, they continually oscillate about their equilibrium position. So these molecules will oscillate like this, but they will not leave its position. So that is the meaning of the solid. So solid has got very huge amount of attraction forces between the molecules. So what is the liquid? The liquid molecular spacing in liquid phase is not much different from that of the solid phase, generally slightly higher. So the molecular spacing, if suppose this is the solid, and for the gas it is little more, but they are also arranged in a systematic way. It is not randomly positioned. So this is a liquid, little more than the solid. So the molecular spacing in the liquid phase is not much different from that of the liquid phase, generally slightly higher, except the molecules are no longer at a fixed position. But here molecules will move in any required direction. It is not random. So they can move much different from the solid phase, except the molecules are no longer at the fixed position relative to each other. So they are not fixed. They can move. But in solid, they are fixed. They only vibrate and they will reach to its equilibrium position. But in the liquid, they will move, but they are not fixed in the one position. If you see about the gas is totally, here we have a lot of molecular distance is more. So the molecules are far apart from each other and a molecular order does not exist. They are haphazard. You see here, just I am drawing. They can go here, they can go this side, they can go in any direction. They can move. So the molecules are far apart, so it is much distance is more than the solid and the liquid. And the molecular order does not exist. Gas molecules move randomly and continually, collide with each other, and the walls of the containers are in. So they will, if this is the container and here is the gas, these molecules will hit the wall of the container where it is posted. They will not be limited. If you see the liquid, if you put at the lowest position, it will sustain. But if it is a gas will go up, down, all the position, it will move. So that is the difference between the solid, liquid and gas, especially the molecular distance between each molecules. For the solid is very, very less. For liquid is slightly more than the solid, but for the gas it is much, much more than the liquid and the solid. So it is haphazarding. The molecules will move, they will hit the wall wherever the gas is present. So that is the phases of the substance. Now I will discuss about the temperature and entropy diagram, and we have discussed a lot on the module 2 what is the entropy and how to find out the entropy, but how to represent in a plot, in a chart. So a TS diagram is the diagram most frequently used to analyze energy transfer system cycles. So it is used to find out energy transfer, in which direction energy is moving. This is because the work done by or on the system and the heat added to or removed from the system can be visualized on TS diagram. By definition of the entropy, the heat transfer to or from a system equals the area under TS curve of the process. So here if you see here, okay, this is the chart here, and here it is the temperature increasing order, and here is the entropy, it is the increasing order. If you see here, for a liquid region, there is a critical point here. So this is the pressure line P4. here is the P2 and this is the P1. It is a solid vapor region, that is ice stream. This is the ice. This is the vapor region here after this dome, and liquid vapor region, that's the water and steam. In this part you will have water and the steam inside this. It is a two-phase region, and beyond this you will have the gases or the steam here, and here you have the liquid, and here you have the solid and the vapor. So this is because and this TS diagram will give the heat transfer. So dQ is equal to T into ds. So change in entropy, and if you multiply by the temperature, you will get how much it is transferred. Transfer of the heat is taking place. So your TS diagram will indicate the heat, how much transfer is taking place. So TS diagram of water is shown here, and a TS diagram of water is shown here. A TS diagram can be constructed for pure substance. It exhibits the same feature as PV diagram. PV. Okay, it is a, this you can see, it is, if you make the PV diagram also, it will be the same way, like this, P and V, and it is like this. It is a vapor zone, it is a two-phase region, and here is the solid and vapor. This is also two-phase region. So we have seen that in the previously also, that this entropy is equal to function of the dryness fraction X into Sg. G stand for the gaseous or the vapor, plus 1 minus X Sf. Sg is a specific entropy for the saturated vapor, and Sf is the specific entropy of saturated water. So this X we can find out, and this is called the dryness fraction. So dryness fraction X is equal to S minus Sf, S minus Sf divided by Sfg, where Sfg is equal to Sg minus Sf. So in this way we have seen for the PV diagram also that we can find out by the help of the temperature, by the pressure here, and then we can get the dryness fraction. Now enthalpy and entropy diagram, it is called the Molar chart. It is the introduction for the Molar chart. Further we will be discussing in our next topic. In next lecture we will be showing some real example, and then we will see it. So here Molar or HS diagram, enthalpy and versus entropy, was a logical extension of the TS diagram, that is a temperature versus entropy diagram, first proposed by Gibbs, retaining the advantages of TS diagram but introducing several new advantages. A typical HS Molar diagram for a thermodynamic fluid such as steam is shown in the figure below. So what is the properties which we can find out by help of this? So here it is enthalpy, it is called H, and this is the S. So here this is the your line, that is the saturation vapor line and saturated liquid line. It is called the saturation line, and from here if you see, this is the here the critical point, and from here the lines of constant dryness, here 0.8, 0.9, and this is a 1. So it is showing the, and if it is here, it may be 7, 6, 5, 4, 2, 1. Okay, so this shows the dryness fraction line. These lines which are parallel to this saturation vapor curve. These are the lines of the constant pressure, and these are the lines of the constant volume. So lines of the constant pressure and the lines of constant volume we can find out, which was not in the TS diagram. In TS diagram only temperature and the entropy, but here pressure, volume, temperature, dryness fraction, all the things we can find out by this, by the help of this chart that is called the HS diagram or the molar chart. This molar chart is available on the steam table. In the steam table, behind that table, one big chart is there, and that chart is called the molar chart or the molar diagram. So what are the advantages of this HS diagram? So the advantages are like this. Vertical lines represent a reversible process and horizontal line represents the constant energy. So if you see here, if you draw a vertical line from here to here, it is a constant entropy line. Entropy line, and this horizontal line, if you draw from here to here, this is the horizontal line, and this is shows the constant enthalpy line. So it shows the, so that is the, so vertical lines represent reversible process and horizontal lines represent lines of constant energy. So these are the constant energy lines, and this is the adiabatic or entropy isentropic lines. Here the entropy will remains constant on the vertical line. From A to B, entropy is constant, and from B to C, the energy is constant. So like this you can find out. Power generation and the refrigeration cycles are most conveniently represented on HS diagram. So for the refrigeration, for the power generation, HS diagram is better to use in place of PV diagram, because work can be calculated directly from the vertical distance as opposed to the area on the TS and the PV diagram. So here the vertical distance from, if it is the HS diagram, this indicates how much work is done. How much work is done or performed directly. If it is going up, means work is done, and if it is going down, work is to be done on the system. Because work can be calculated directly from the vertical distance as opposed to the TS and the PV diagram. In TS and the PV diagram, we have to use the area. This is the PV. So work is equal to PdV. But here it will give you the H. So work is equal to H2 minus H1. This indicates the work. So directly, if you reduce enthalpy from final to initial, you will get the work done by the system. So that is the advantage of this system. Now HS plot, an example. Just I am showing here one Rankine cycle. So Rankine cycle of a turbine system in molar diagram. Inefficiencies due to irreversibility in the real process are shown clearly on the HS diagram as shown in the figure below. So here this you can see here that 1 to 2 is the turbine. In the turbine, expansion is taking place. From 2 to 3, it is a condenser where this thing is at constant pressure. It is heat is removed. Then the pressure is increased on the pump. From here, it is going to the furnace where the heat is added. So this you can see here that from 1 to 2, this is the ideal process where the entropy is constant. But in the real scenario, it will not be a straight line, but it will be having some slant line like this. So 1 to 2, it is a turbine output. So from here, if it is the H1 and this is the H2, so H1 minus H2 is work obtained by turbine. Directly you can find out. So that is the, so this is, so it's supposed to be here, but it is coming here. This much turbine losses are there. These are the losses. It may be 5 to 10% losses on the turbine due to the entropy is not remained. Delta S is not 0, or entropy is not remain constant from 1 to 2 dash. Now it will go from 2 to 3. It is a low pressure condensation. So it is happening here. So in this, at the low pressure, the condensation, the heat is removed from here to here. You reach at the point 3. Point 3 to 4, the enthalpy is increased. Work has to be done. In the turbine, we are obtain the work. But here, 3 to 4, the turbine will give some part of the work. It is a 3 to 4. And from 4 to again 1, it is furnace, a hot like boiler. This is the boiler. In the boiler, the water is heated and you are getting the work done. So like this, you can draw, and in this, all vertical lines, they will represent directly work. Or it can also show by the first law of the thermodynamics, that del Q is equal to del W. And this is H2 minus H1. So that is the benefit, and this example shows that how we can represent any process, any real industrial problems like thermal power plant or gas turbine engines, we can represent in HS plot as described. So here I have shown the Rankine cycle, but you can make the Brayton cycle or any refrigeration like Bell-Coleman cycle and all, you can represent in this HS diagram. Next we have one special, it is known as a PVT surface, pressure, volume and temperature surfaces. So in one plot, we can get all the three. Normally, as of now, we have seen the PV diagram or TS diagram or TP diagram. Only two variables are there. But here in this plot, you can see that all the three important properties of a substance are depicted in a one diagram, and that is called the PVT surfaces. So the PVT surface shown for a material that contracts on freezing. The surface is described by the equation of state of the material and is the locus of all equilibrium states of the material. The diagram shows regions associated with solid, liquid and the gas phases. So this you can see here that this is the here liquid and this is the solid and the vapor, and beyond that this area is gas zone and this is the liquid zone. As we have seen in our PV diagram also, same way it is a PV or TV. If you see TV also, so it is like this. So same way this you can see all P volume and here is the temperature, and accordingly we can find out all the parameters of this any substance. So regions in which two phases coexist are normal to the T and T. Planes as in such region, isotherms and isobar are identical. So in two-phase region, if you see here, pressure and the temperature lines are identical. They will overlap to each other. So you cannot identify. So because both are moving together and they are the same. As a phase change take place, material goes from one phase to the other and the volume of the system changes. But in this phase, volume will change. Pressure and the temperature will remain the same. If you see here, this. Here also, in this zone, volume will increase. V1 to V2, where V2 is greater than V1. So if you increase the temperature or the pressure, your volume will opposite to the pressure and it is directly proportional to the temperature. The Gibbs function is the same for the two-phase in equilibrium. So in the two-phase region, the Gibbs function will remain the same. It is shown here in a very colorful manner. It is taken from the reference one. So here, if you see here, this is the solid and the vapor zone. Here is the critical point here, critical state. From the critical state, if you move towards the left, it is a liquid, and if you move towards the right, it is a vapor or the gaseous vapor or gas zone, and between this two line it is a mixture of liquid and the gas. Here we have the triple point here. In this point you have the solid, you have the liquid, and you have the gas. So it is called the triple point state, and here it is called the critical state. So critical state you have the temperature and the pressure high, but in the triple state it is a very low temperature. So for the different material you have the different. Here we have the constant temperature lines are these are the constant temperature lines. This is the critical temperature. Here you have the constant pressure line. Solid and the liquid here. Solid and the liquid. This is the solid and the liquid zone. And this is the constant pressure line, and this is moving from here in this way. Here it will remain. If you see, this is the temperature line. This is the T and this is the P, and both are moving in the parallel. There is no change in the pressure and the temperature in the liquid to liquid and the vapor zone. This type of all the three parameters, that is pressure, volume and the temperature, can be represented by this PVT plot. So that is the advantage of this plot, and very useful for identifying the behavior of the substance when the pressure, temperature and the volume are changing. Now I will discuss about the triple point. I have seen here, this is here, we have the triple point. So what is the significance of this point? I am going to discuss in this slide. So the triple point represents the combination of pressure and the temperature that facilitate all phases of matter at equilibrium. So in this, the pressure and the temperature. So what is the pressure and the temperature? That represents the all the three phases. The critical point terminates the liquid and the gas phase line and relates to the critical pressure, the pressure above, which is supercritical fluid form. So if you see here that phase diagram, so this you can see that here we have here liquid, here we have the solid, we have the liquid, and here we have the gas, and this all things are present at this. So this is called the triple point. And phase diagram of it is for the carbon dioxide, it is somewhat higher temperature, you will get the solid, liquid and the gas. But for the water, this triple point is very low, 0.006 atmospheric you will get, but this is nearly 5.2 atmospheric, means above atmospheric pressure you will get the triple point, but for the water you will get a very less pressure at 0.006. So that is the difference of the water and the carbon dioxide. For the carbon dioxide you have the high triple point, and for the water you have the very low. For some other liquids and the gases you have further low. So dryness fractions. What is the dryness fraction? We have seen just now that dryness fraction is defined as the ratio of mass of dry steam, that is the vapor, to combined mass of dry steam, that is the vapor, and mass of the liquid steam. It is denoted by X. The value of the dryness fraction lies between the 0 and 1. So means 0 means pure water, and or it is called saturated water, and 1 means it is saturated vapor. Saturated vapor. So we can define the dryness fraction that out of total mixture of water and the vapor, how much mass of the vapor present in the mixture divided by the total mass. The total mass include the mass of the vapor plus mass of the liquid. So mass of the vapor is represented by mv and the mass of the liquid is represented by ml. So here if you see here, so for saturated dryness, for the saturated liquid, dryness fraction x is equal to 0, and for the saturated vapor x is equal to 1. So if you see, this is here x is equal to 1, and for here it is x is equal to 0. But what will be here? This you can find out by help of this. So this indicates that in the given system, how much is the mass of the vapor and how much is the mass of the liquid, that it is represented here, and this value of this dryness fraction x lies between 0 and the 1. So here it is called the saturated liquid, and here x is equal to 1, and it is called the saturated vapor, here x is equal to 1. So here we have depicted the dryness fraction of the given, but here you can find out by help of this equation that x is equal to here mass of the mv divided by mv plus ml, where v is the vapor and l is the liquid. So it is a total mass of the mixture, and here is the total mass of the vapor. So mass of the vapor divided by total mass of the mixture is called the dryness fraction, and to calculate the energy, to calculate the work done, to calculate the heat added, we need to find out x. Without x we cannot find out the full state of the system. So in the next class I will be discussing about molar chart, then I will discuss about psychrometric properties, then I will discuss the dry bulb temperature, then wet bulb temperature and dew point temperature. These points I am going to discuss in my next class. Be tuned for that. These are the references I have taken from P.K. Nag, Engineering Thermodynamics, Tata McGraw-Hill's, Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach. Then NPTEL lecture from Dr. D.P. Mishra, IIT Kanpur. Any questions you are welcome to ask. So my email is ydvedi@gmail.com. You are always welcome to like and subscribe my channel. If any query, you can send in this mail or comment on this given YouTube video. Till then, goodbye and thank you very much for the joining. Be tuned. I will be discussing the topic which I have just now described. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.